In the previous lesson, we became introduced to L'Hopital's rule, which said that if you want the limit of something like this, 3x over x, as x goes to infinity, then we noted that the rate of growth of these things is a ratio of 3 to 1. This is always 3 times as great as this one, so as x goes to infinity, you could basically just divide those out. Or another way of thinking about it, since the rate of growth of this is equal to the rate of growth of that one, we kind of focus in on those rates of growth, and we say that the derivative of this, which would be 3, over the derivative of this, which would be 1, as x goes to infinity, is equal to 3. Okay, so we do it either simply or using L'Hopital's rule. We can do the same thing when we take the limit as x goes to 0. As x goes to 0, this one will still be 3 times as high as this. So here, we're going to have 3x over x. In this case, both of these things are going to 0, but the ratio, again, is always 3. So again, we're looking at the rates of growth, or in this case, the rates at which they're getting small. And so L'Hopital's rule allows us again to take the derivative of each one, and in this case we get 3 over 1 again over 1, which is 3. So L'Hopital's rule applies not only when you have something of the form infinity over infinity, but also when you have something of the form 0 over 0. Well, of course, this one was simple to do without L'Hopital's rule. I just used it to illustrate. But let's look at another example. Here's a case where, if you think about what 1 minus cosine, just cosine of x. 1 minus cosine of x looks like. Cosine, of course, looks like this. Minus cosine looks like that. And if you add 1 to it, it's going to look like this. So 1 minus cosine of x looks something like this, and x looks something like this. So similar to 3x over x, they're both going to 0. But in this case, notice, similar to what we looked for with those things going to infinity, they're coming in towards 0 at different rates. This is zeroing in like a jet plane coming in for a landing, whereas you wouldn't want to land on a plane coming in like this. This is coming in tangent, this is coming straight down. So it looks like the ratio, as you get close to 0, the ratio of this to this might be 0. Okay, unlike x and 3x, where they're just coming in at different rates. Here it looks like this is coming in tangent to the graph, whereas this isn't. So notice we still have 0 over 0, and so L'Hopital's rule still applies. You can take the derivative of each one. Derivative of 1 is 0. Derivative of negative cosine of x is sine of x. The derivative of x is 1. And now we see that as x goes to 0, you get 0 over 1, which is 0. So sure enough, L'Hopital's rule allows us to get the answer to one like this too. We could have done this one a different way. We could have multiplied both the top and the bottom by the conjugate, and then gotten 1 minus cosine of x is sine squared of x over x, and then written that as sine of x over x times sine of x. And then as x goes to 0, recall this goes to 1, and this goes to 0. So we could have gotten the answer without L'Hopital's rule, but the point is L'Hopital's rule gives us the right answer. Okay? And there's no reason why similar to the problems yesterday. No reason why this has to be a 0 here. Okay, so notice, oops, yeah, at 2. As x approaches 0, put in a 2 here. The top goes to 0. 4 minus 10 plus 6 is 0. The bottom goes to 0. 4 plus 2 is 6, minus 6 is 0. So we can use L'Hopital's rule. Take the derivative of the top, get 2x minus 5. Take the derivative of the bottom, 2x minus 3. Now as x approaches 2, you're going to get 8 minus 5 is 3, over 4 minus 3 is 1, is equal to 3. Well, we're having lots of 3's here. So again, it's kind of a cool case where you can use L'Hopital's rule, and you get the answer. Now, as I say, this one you could have done either way, but suppose we have a problem like this. This is one of my favorite ones. Five to the 0 is 1, 2 to the 0 is 1. So 1 minus 1 is 0, 0 over 0. So it's of the form where we can use L'Hopital's rule. So we can take the derivative of both the top and the bottom. Notice this is not the quotient rule. We're not thinking of this as one big function. We're thinking of it as the ratio of two functions. We're thinking of it as one function divided by another one, and we're dealing with each one independently. So, so how do we take the derivative of the top? The key to that is to realize that a to the x is equal to e to the x times the ln of a. Why is that? Because if I bring the x up here, e to the ln of anything is just that thing. So this is a real handy identity to keep in mind. Okay, you just leave this right where it is, and you take the ln of that, and then you put an e right there. Okay, so I'm going to first rewrite it. E to the x ln of 5 minus e to the x ln of 2 all over x. I haven't used L'Hopital's rule yet. All I've done is rewritten it. But now I can use L'Hopital's rule. Let's see. The derivative of e to anything is e to that thing times the derivative of the top. What's the derivative of the top? Do you need to use the product rule here? If you said yes, think again. This is just a constant times x. And the derivative of a constant times x is just that constant. Similarly, e to the x ln of 2 times the derivative of the top is the ln of 2. Now the derivative of x is 1. And so now as x goes to 0, e to the 0 is 1, e to the 0 is 1. So we get the ln of 5 minus the ln of 2 all over 1, which if you want to, you can write as the ln of 5/2. Not something you would have guessed at for an answer. So there's a nice case of using L'Hopital's rule. Okay? So as long as I've been using it now, let me just let me write it down just so you got it. Here's what L'Hopital's rule says. It says you take the limit as x approaches anything. It doesn't matter what that is. It could be 0, it could be 2, it could be -5, it could be infinity, minus infinity, it doesn't matter. And if you have two functions, and each one of those things either goes to, I'm including what we learned yesterday as well, infinity over infinity or minus infinity over infinity, it doesn't matter because the negative you could just bring out front anyway. So either they're both going off to infinity, or if they're both going to 0, those are the two cases where you can use it. Then L'Hopital's rule says that you go ahead, I'll just use a here, and you take the derivative of each, and whatever that limit is, that's the limit of the original one. Okay, so a very powerful and cool theorem. Okay, so I've shown you a couple ways in which we had to use it. Let me show you a couple other problems that are all kind of important. How about this one? Okay, what do we have there? Notice that as x goes to infinity, the thing inside is going to get big and the ln will get big. So this is something of the form infinity minus infinity. We already looked at one of those a while back when we looked at x squared plus x minus x. We looked at the limit of that as x went to infinity. Remember, we multiplied by the conjugate, and we got that the answer to that was 1/2. Kind of surprising. So we did that one without L'Hopital's rule. This one, we really don't need L'Hopital's rule either, but we can use it. The key to this one, the key is to use the property of logarithms. Oops, I meant to have an x squared there. There you go. So now as x goes to infinity, if you want to, you can use L'Hopital's rule just on the inside. Or, in this case, it's silly to use a sledgehammer to kill an ant. And L'Hopital's rule is like a sledgehammer. It's a powerful piece of machinery. Here, all you have to do is divide both the top and the bottom by x squared. And you're going to get 5/2, the ln of 5/2. So go ahead and try L'Hopital's rule on that, on the inside, just on the inside, and you'll end up with 5/2 as well. But anyway, so your answer is the ln of 5/2. Okay, so that's kind of an interesting one to be aware of. How about this one? This is one of my favorite ones to put on a test. Okay, we know what the derivative of cosine is. We know what the derivative of x squared is. But remember, before you use L'Hopital's rule, you need to make sure that it's workable. As x approaches 0, the cosine of x approaches 1, and x squared approaches 0. Whoa! We can't use L'Hopital's rule. That's the bad news. It's not of the form 0 over 0 or infinity over infinity. That's the bad news. The good news is we don't have to use it. Because just think about it. Don't lose your common sense as you learn big rules. This thing here, cosine, is approaching 1 from both sides. It's getting closer and closer to 1. X squared is getting closer and closer to 0. Always positive and smaller. What happens is you take a number close to 1 and divide it by a really small number. It goes off to infinity. So there's the answer. So don't lose track of things. Calculus and mathematics is not a bunch of rules to apply. It's an understanding, and the rules are there to help you as you need them. Let's try another one. This one is of the form infinity over infinity, so we can use L'Hopital's rule on it. The derivative of the top is going to be 1/2 times x squared plus 1 to the subtract 1, you're going to get that, times the derivative of the top of the inside, which is 2x. Bottom, the derivative of the bottom, x is just 1. So this goes with this, And notice what we end up with. We end up with x. Okay? That's one of my favorite problems too. Use L'Hopital's rule on it and it doesn't get you anywhere. It just flips it over. If you use L'Hopital's rule again, it would flip it over again. So that's of no use at all. That's the bad news. Again, don't lose your common sense, okay? Remember what we already learned back when? We said, oh, all you have to do is divide by the highest power of x on the bottom. Sometimes these work. Bring the 1 over x in. It's going to come in as 1 over x squared. X squared over x squared is 1. Plus 1 over x squared. At the bottom you're going to get 1. Now as x goes to infinity, the answer is 1. Okay, so these are cases where you don't use it. Finally, I'll do one more on this lesson, and that's going to be so recall that the time when you use L'Hopital's rule is when you have something of the form one function divided by another. And we don't have that there. See that? So it doesn't look like it's a candidate for L'Hopital's rule. Notice that I can only approach 0 from the right because the ln is only defined for positive values of x. So what can we do? Here's the answer. Again, take a moment, turn off the video if you want. Pause it. Here's what you can do. You can do this. Just a little algebraic trick. You take the x there and you put it as a 1 over x in the bottom. Because this thing can just be flipped up again, so algebraically they're exactly the same. Nothing you would ever think of doing, but notice that as x goes to infinity, as x goes to 0, the top goes to minus infinity, and the bottom is going to go to plus infinity. So a great place to use L'Hopital's rule. It doesn't guarantee that it's going to work, but I happen to know that it will. So you take the derivative of the top, take the derivative of the bottom is x to the minus 1. If you take the derivative, it's going to be minus 1 over x squared. Well shoot, as x goes to 0, you still have infinity over infinity, plus or minus. So did we get anywhere? Sure we did. Don't forget your algebra. So this is where we use L'Hopital's rule, right there. So now we're not using L'Hopital's rule. All I'm doing is keeping track of my algebra, and I can bring this upstairs. It's going to be negative x squared over x. One of the x's cancel. I get negative x as x goes to 0. I get 0. So that limit goes to 0, which is not at all obvious. What we're saying is if we take the function x, which looks like this, and we take the function ln of x, looks like this, and these things here get closer and closer to 0, and these things here go off to minus infinity, it's just not clear what's going to happen when you multiply these numbers. But apparently, in this case, this one wins out. It doesn't even compromise. Remember some of those other ones compromise to e or to 1/2 or so on? This one doesn't compromise. This thing wins, and you get that. So, there's the rest of L'Hopital's rule. And in the next lesson, now we're going to use that to find some really interesting limits. Okay, they're called indeterminate forms. In fact, I'll mention it right now. And this is where we'll pick up in the next lesson. Very good.